India, a nation of over 1.4 billion people, is facing a pressing challenge: the energy crisis. More than 75% of India's energy needs are met by fossil fuels like coal and crude oil. A major chunk of this is imported, which leaves us heavily reliant on foreign fossil fuels. This not only damages our economy but also leaves us vulnerable to geopolitical tensions and global market fluctuations. Meanwhile, the need to generate clean and sustainable energy has never been greater before as the world grapples with adverse effects of climate change. Amidst all these challenges, there is an incredible opportunity for India. Yes, thorium. But how does this solve India's problem? Welcome to Snap, where we break down science to its simplest blocks. India is home to one of the largest reserves of thorium. More than 25% of world's thorium reserves is present in India. This underutilized element has the potential to revolutionize India's energy landscape, thereby paving way for India to become a global superpower. But if you're wondering how a single chemical element can change the fate of an entire nation, then you need to know about one man, a visionary, a legend, the father of Indian atomic science, Dr. Homi Jehangir Bhabha. More than 70 years ago, this man laid the foundation of India's revolutionary three-stage nuclear program, a roadmap designed to harness the vast potential of thorium, which is abundantly available in India. In this video, we'll explore Dr. Bhabha's vision, how thorium fits the bigger picture, and what it takes to make India an energy supergiant. To understand why thorium is so important, let's break down how electricity is predominantly generated. Excluding clean energy resources like wind or sun, it's all about converting heat into electric power. So how is heat generated? Well, you can either generate heat by burning coal in a thermal power plant, or by nuclear fission, where an atom splits and releases tremendous amount of energy which transforms to heat. So what do you do with this heat? Well, you can turn water into steam with this heat, which is fed to a turbine. This turbine is in turn connected to a generator where a rotating coil under a magnetic field produces electricity. It's that simple. Heat, steam, motion, and electricity. But here's where the major challenge lies. Coal plants are heavily polluting, releasing massive amounts of carbon dioxide and particulates. It is also very poor in efficiency. It has about 33 to 40% of thermal efficiency, which means most of the heat energy generated by coal is consumed by the coal itself. On the other hand, traditional nuclear fuels like uranium is much more cleaner, but it's not very efficient as well. Uranium reactors operate at a thermal efficiency of 30 to 35%, and there's the problem of radioactive waste. Also, uranium is a finite resource with limited reserves. So how does thorium solve all these problems? Well, thorium is 3 to 4 times more abundantly available in nature than uranium. Thorium reactor designs have a promising thermal efficiency of 45 to 50%. And lastly, nuclear reactors which use thorium as a fuel produce far less radioactive waste compared to uranium. Before we dig deeper into India's three-stage nuclear program, we need to understand what nuclear fission is. But before we understand what nuclear fission is, we need to understand what are heavy atoms and what are isotopes. So, an atom consists of predominantly three particles: protons, neutrons, and electrons. The protons and neutrons form the nuclei which lies at the center of the atom, and the electrons revolve around it. Here's the most important part. The number of protons determines which chemical element it is. For instance, hydrogen has 1 proton, helium has 2, and so on and so forth. All the elements in the periodic table are arranged in their increasing order of number of protons in their atom. Now, when an atom has a large number of protons and neutrons in its nuclei, that's when we call it a heavy atom. So what are isotopes then? While the number of protons of a chemical element can never change, that's not the case with neutrons. A same chemical element can have different number of neutrons, and that's when we call it isotopes of that element. Take uranium for example. Uranium can have 143 neutrons, which makes it U-235. And it can also have 146 neutrons, which makes it U-238. In both cases, the number of protons is 92. Because it's a uranium atom, if the number of protons change, it cannot be called a uranium anymore. So why are isotopes so important? Because the entire nuclear science lies behind neutrons and operating with isotopes of the same element. The number of neutrons determines whether an element is fissile or fertile. Well, what are they? A chemical element can be called fissile when it is ready to undergo nuclear fission, whereas fertile elements just can't. Please remember, the same element can be fissile or fertile, all depending on the number of neutrons in it. Why does this matter? Because nuclear fission depends on certain isotopes being unstable enough to split when hit by a neutron. For instance, uranium-235 is fissile, meaning it easily undergoes fission, while uranium-238 is fertile, which means it cannot undergo fission. Now, back to nuclear fission, the process at the heart of nuclear power. Nuclear fission occurs when the nucleus of a heavy atom like uranium or thorium splits into smaller nuclei after absorbing a neutron. This splitting releases massive amounts of energy in the form of heat, along with more neutrons. These neutrons can then collide with other nuclei, causing a chain reaction. This chain reaction is what powers nuclear reactors. The heat produced is used to generate steam, spin turbines, and ultimately produce electricity. Fission is incredibly efficient. A single gram of uranium or thorium can produce as much energy as several tons of coal. Alright, now that we have covered the basics of nuclear science, let's get into what India's three-stage nuclear program is. Before that, let's first answer the question, why do we need three stages? In order to answer that, we'll first look into what the third stage aims to do. The third stage nuclear reactor, or the advanced heavy water reactor, uses U-233 as a nuclear fuel. While U-233 undergoes nuclear fission and produces heat, we will be introducing Thorium-232 inside the reactor. Thorium-232 then absorbs a neutron from this fission process and decays into further Uranium-233. This is a sustainable chain reaction where we only have to refuel thorium from time to time. Great! So why don't we do it already? Why do we need the first two stages? Well, that's because uranium-233 is not available naturally. It can only be a byproduct of stage 2. So what is a stage 2 reactor? Stage 2 reactor, or FBR, which is fast breeder reactor, uses plutonium-239 as primary fuel for nuclear fission. These reactors are designed to breed more fuel than they consume. This converts uranium-238, which is abundant but not fissile, into more plutonium-239. At the same time, thorium-232 is also introduced, which gets converted into uranium-233 through a nuclear reaction. Alright, this sounds good too, but why do we need stage 1? Why don't we directly implement stage 2? Well, you guessed it right. Even plutonium-239, which is the primary fuel for stage 2, isn't available naturally. It is the byproduct of yet another fission reaction that happens in stage 1. So, what is stage 1? Stage 1 uses PHWR, which is pressurized heavy water reactors. In this stage, natural uranium, or U-238, which contains only about 0.7% of fissile uranium-235, is used in pressurized heavy water reactors. These reactors generate energy and produce plutonium-239 as a byproduct. Plutonium-239 is another fissile material crucial for the stage 2 of the program. Now, do you get the full picture? In the first stage, uranium-235, which is present in natural uranium or uranium-238, is used to produce plutonium-239. In the second stage, this plutonium-239 along with uranium-238 produces more plutonium-239. While this is happening, thorium-232 is inserted into the reactor, which decays into uranium-233, which is the primary fuel for the next stage. In the third stage, uranium-233 is used as a primary fuel for nuclear fission, but It can be refueled by filling in more thorium-232, which again decays to become uranium-233, hence making it a self-sustaining process. Alright, now that you've understood the science behind the three-stage nuclear program, let's look at where we are today. Currently, India is amid stage 2 of its three-stage nuclear program. The Indira Gandhi Center of Atomic Research, or IGCAR in Kalpakkam, Tamil Nadu, is spearheading this effort with its prototype fast breeder reactor. Once operational, the PFBR will play a crucial role in bridging the gap between stage 2 and stage 3. However, transitioning into the stage 3 is not an overnight process. Experts estimate that close to 2 to 3 decades of steady operation of PFBR is needed before we fully migrate to third stage, thereby achieving a sustainable thorium fuel cycle. Understanding India's three-stage nuclear program highlights the brilliance and vision of Dr. Homi Jehangir Bhabha. He devised this ambitious strategy not in today's era, where energy crisis dominates global conversations, but in an era where India was struggling with poverty. Let us take pride in the fact that we are steadily walking towards becoming an energy supergiant, and the future is not far away. And we've come to the end of this video. For the sake of sticking to the scope of this video, we've oversimplified a lot of scientific concepts. If you're interested in knowing about any of them in detail, let us know in the comment section and we'll make a video about it. Thanks for watching. For more awe-inspiring stories of science and tech, follow Snap.